Welcome everybody to the Astronomical Society of Edinburgh. Welcome everybody, and to our evening online meeting that we have each month. Uh, uh, just a few before we get to our speaker, we for tonight, just a few small announcements. So I will be looking at what we have coming soon in our talks program, and then after that, I'll hand over to Dr. Sarah Hörst of Johns Hopkins University, where she's going to be telling us about her research activities with toxic Titan. So on the 2nd of May, we at our meeting, which is held in the centre of Edinburgh, at the Augustine United Church on George IV Bridge, we'll be having our in-person meeting where Professor Vicky Fawcett will be speaking to us about observing the brightest objects in the universe. And the following week, on the 7th of May, we'll have our usual online imaging and observing group, which is open to members of the society. And then on the 16th of May, to finish off that month, we will be having, again, it's an online meeting. We will be having Dr. Julian Onions, who will be asking the question, cold, dark matter. Is it cold, is it dark, and is it matter? So looking forward to all of these things. So now I would like to, without further ado, welcome Dr. Sarah Hörst, who will be talking to us this evening about toxic Titan. Over to you, Sarah.
All right, we got Zoom to work once before. Let's see if we can get it to work again. There we go. Can you see my slides okay?
Yes, we can.
Perfect. All right. Thank you so much for having me. I realized very belatedly that it's Easter weekend, and so hopefully that didn't affect people being able to participate tonight. So I'm gonna talk to you today about Titan, which is the largest moon of Saturn. And the way that I'm gonna kind of tell this story is the way that I tend to think of my job as a planetary scientist, which is to turn the points of light that we see in the night sky when we go outside, um, into worlds that we can study using the same tools, and same equations and everything else that we use to study the Earth. And then, to talk about what the implications are there and what the big picture questions are that we're trying to answer by turning those points of light into worlds. Um, so stepping way back, Titan was discovered by Christian Huygens in 1655. You can see his discovery drawings in this manuscript that he wrote about the Saturn system. And basically, what happened was he looked at Saturn, repeated observations night after night, and realized that there was, something that was moving in this kind of regular pattern. And he was smart enough to recognize that um, that object must be orbiting Saturn and that it was a moon. But obviously, it was just a point of light. With the telescope that he was able to use, Saturn kind of just looks like a dot with ears, a phenomenon that I assume probably most of you are quite familiar with. And so then Titan was really just, this little dot orbiting the circle with ears. After that, really nothing of note happened for a long time. We were still really waiting for telescope technology to advance and mature to the point where we were really able to learn a lot more about the kind of smaller size objects in the solar system. So our next big advance, going from 1655, didn't happen for about 250 years. And the next thing that happened was in the early 1900s, there were some observations that were made in Spain of Titan. And when the observations were described, and this is obviously a drawing, not a picture, they were described as having limb darkening. And limb darkening is a phenomenon that we see because atmospheres are made of gases, and the solid planets are made out of solids. And so when light interacts with the solid part of the planet, obviously it can't go through. But when light interacts with the gases on kind of the limb of the planet, some of the light is able to go through. And so the solid surface looks different than the edges of the disk where you have the atmosphere interacting with light. And so this was suggestive of an atmosphere. There's a lot of debate in the community about whether or not this particular telescope would have been sufficient to actually recognize limb darkening on Titan. The astronomer in question was known to have really good eyesight. And at the time, with the telescopes as they were, your own personal eyesight actually mattered quite a bit for what you were able to see. And so it's quite possible that maybe he was one of the people that would be able to see this phenomenon with the telescope. But certainly he was the first person to mention the idea that Titan had an atmosphere. Um, and then nothing happened again. Patience is definitely a virtue when you study the outer solar system for about 36 years, 37 years. And the next thing that happened then was the definitive discovery of Titan's atmosphere, which is shown here. So Gerard Kuiper, whose name is famous because of the Kuiper belt, was looking at all of the giant planets. So he was looking in particular at Jupiter and Saturn, and then he was looking at their large moons. So he was looking at Callisto, Europa, Ganymede, and Io, the largest moons of Jupiter, and then he was looking at Titan, which is the largest moon of Saturn. And immediately, one thing really jumped out at him was that Titan looked more like Jupiter and Saturn than it looked like the Galilean satellites. And so this is a spectrum that was taken in the infrared, showing some absorption bands that were shared um, between Titan, Saturn, and Jupiter, and not the four Galilean moons. And what you're seeing here actually is the spectroscopic signature of methane. And so this is the definitive discovery of an atmosphere around Titan. Kuiper wrote a paper called Titan, a Satellite with an Atmosphere. I always feel like there's punctuation missing at the end of that title, like an exclamation point or a question mark, because this turns out to be a really big deal. And the reason for that is shown here. So this is one of my favorite graphics that was made by Emily Lakdawala while she was at the Planetary Society. And this is her collection of what she likes to call the not planets. So these are all of the objects in our solar system that are spherical, but for one reason or another do not fit the IAU definition of a planet. And Titan is front and center in the middle, kind of showing why it's so weird. So all of the other not planets that you see in the solar system, you see impact craters. On Io, you can see the volcanic features. On Europa, you can see a lot of the fracture features that we think are kind of distinctive of the fact that it has this subsurface ocean. And when you look at Titan, you don't see anything because Titan has this very thick atmosphere. And so it turns out that Titan is the only moon in our solar system that has a substantial atmosphere. And just from that piece of information, we immediately know that Titan is a really interesting object that definitely warrants further study. So 1944, we discover that Titan has an atmosphere. This is, of course, the royal we. I was not born in 1944. The next thing that happened were the Voyager spacecraft. So the Voyager spacecraft flew through the Saturn system in the early 1980s. One of the flybys was actually specifically designed to study Titan in greater detail because we already had this sense that Titan was going to turn out to be really important, even though we had very little information. And this is the one of the images that was sent back by the Voyager spacecraft. I always like to joke that you too can recreate the Voyager flyby of the Saturn system in the comfort of your own home with an iPhone and an orange. You'll actually get a much higher resolution image and approximately as much information as we got from this picture that Voyager sent back of Titan. Luckily, Voyager was carrying other instruments besides the camera, and in particular, it was carrying an infrared spectrometer. So again, looking at the infrared wavelengths to understand the composition of our atmospheres, just like Kuiper did. And from that infrared spectrum, we discover that Titan's atmosphere contains a lot of organic molecules. And so when I say organic now and through the rest of this talk, what I just mean are molecules that contain carbon, and in particular molecules that contain carbon that is bonded to a hydrogen atom. And so Voyager discovered the presence of a number of these organic molecules in Titan's atmosphere. So There's acetylene if you're, into welding. There's propane if you want to have your friends and family over for a barbecue this weekend. There's hydrogen cyanide if you don't like your friends and family very much. And so there's this whole host of organic molecules. And so this set of data taken together turned out to be um, really frustrating to planetary scientists at the time because we know that this atmosphere is full of all of these organic molecules. This is the most organic molecules we'd seen in any atmosphere besides the atmosphere of Earth, which obviously has life on it. But of course, we can't see down to the surface because of Titan's thick atmosphere. So there could have been, 12-foot tall Titanians jumping up and down and waving at the Voyager spacecraft, and we would not have known. And so kind of immediately after um, the Voyager flybys, people started work on the next mission to study the Saturn system, and in particular, the next mission to study Titan. Um, just to pause for a second and get everybody on the same page about a couple of things that we know about Titan. Um, Obviously, the big thing with the rings is Saturn. I trust that you all know that already. Titan is the little brown dot that's kind of down towards the bottom of the slide. Um, Titan is the largest moon of Saturn. It has a diameter of about 5,150 kilometers. That makes it the second largest moon in the solar system. We lose out just slightly to Ganymede when you look at the solid surface radius. If you include Titan's atmosphere, Titan's actually bigger than Ganymede. But at any rate, it is bigger than the planet Mercury. It's bigger than our own moon. So even though it's kind of dwarfed by Saturn, it is a very substantial object. It has a mass of about 0.0225 Earth masses. If you take that mass and radius together, that gives us a density of about 1.9 grams per centimeter cubed. That means it's about half rock and half water ice. We know now from subsequent data taken by various spacecraft that Titan is at least partially, if not fully, differentiated. So that means, like Earth, most of the denser material, which in this case is rock, has moved deep into the planet. So it has a core that's made out of rock, and the surface is made out of water ice rather than rock. The surface temperature is a balmy 94 Kelvin. I have no idea what, well, you guys don't care about Fahrenheit, but I don't know what it is in Fahrenheit because it doesn't matter. It's cold. It's so cold that it doesn't mean anything to any of us. The surface pressure is about 1.5 bar, so that's 1.5 times the pressure here on Earth at sea level. And as I mentioned already, it's the only moon with a significant atmosphere. So one thing to note about this, we're going to do a bunch of chemistry today, which I realize is weird for astronomers, but it's going to be okay. I believe in you. We can do it together. So you may not have seen one of these since you were in school, or you may never have seen one of these, but this is what's called a phase diagram. And it is basically looking at different pressures and different temperatures and telling us what phase of matter we would expect things to be in. And this is one for methane. And that little red T, you can probably already guess, is the location of Titan's surface conditions. Titan's surface temperature and pressure is very close to what we call the triple point of methane. The triple point is the place where all of the phases of matter can exist simultaneously. So solid, liquid, and gas can all exist together at the same time. Earth is very close to the triple point of water. That's one of the reasons why we get this horrible thing called wintry mix, where it's like snowing and raining and doing all of those things all at the same time. But it's also what allows the water cycle to happen on Earth. And so even just knowing the pressure and temperature at Titan's surface tells us immediately that something really interesting might be going on with the methane on Titan. And that turns out to be correct. We'll talk about that more in a little bit. So I already mentioned that Titan's atmosphere is very thick. We talked about the methane already that was discovered by Gerard Kuiper, but it turns out that that's actually not the main constituent of Titan's atmosphere. So Titan's atmosphere is only about 2% methane. The rest is molecular nitrogen, about 98% molecular nitrogen. Molecular nitrogen cannot be measured from remote sensing. It does not interact with light in a way that is useful to us for being able to measure it from telescopes. And so that is why Gerard Kuiper measured the methane but did not measure the nitrogen because it just isn't something that we can do from remote sensing, which presents a really big challenge. We were kind of talking a little bit at the beginning about this new exoplanet discovery, and this is one of the challenges in trying to do remote sensing. There are certain molecules that just can't be measured using telescopes. when the methane and nitrogen in Titan's atmosphere interact with light, they undergo something called photochemistry. So light breaks up the methane and nitrogen into pieces that are highly reactive. Those pieces run around and make new friends and build new molecules, and we get things like hydrocarbons, which are just molecules containing carbon and hydrogen, and nitriles, which are just molecules that contain carbon and nitrogen. Those molecules will then subsequently react with each other to keep building bigger and bigger molecules until we get haze particles, which are kind of like smog on Earth. It's the same process that's kind of characteristic of Titan and is really highlighted in this image. The other thing to note about Titan that's going to be important for some of the questions that go on to turn out to be really interesting for us is that it does contain some oxygen-bearing molecules. So there's carbon monoxide, carbon dioxide, and water. Those are in order of decreasing abundance. So the most abundant of those is carbon monoxide. It has an abundance of 50 parts per million. Excuse me. That doesn't sound like very much, but that actually makes carbon monoxide the fourth most abundant molecule in Titan's atmosphere. So one of the reasons that we care about that, I mentioned that we have all these hydrocarbons and nitriles. So all of life on Earth is built on the same small set of molecules, speaking of astrobiology. Um, so all of life on Earth is built on the same small set of molecules. Molecules that we tend to think of are things like amino acids, which are the building blocks of proteins, and nucleobases, which are the building blocks of DNA and RNA, and also some of our energy-containing molecules. That small set of molecules that all of life on Earth, from the smallest to the largest creatures, share are built on the same small set of atoms. The smallest set of atoms that we tend to think of as being important when we're thinking about origin of life and search for life chemistry are carbon, nitrogen, hydrogen, and oxygen. We have all four of those atoms present in Titan's atmosphere participating in organic chemistry. And so, kind of immediately, we know that this is going to be a place that's going to have a lot of important questions for us about the origin and evolution of life and also the search for life. So, I told you that right after Voyager, everybody was like, sweet, we got to build a new spacecraft. Let's go back to Titan. But again, patience is really a virtue. So, Voyager flybys were in the early 1980s. Work immediately started on what eventually became the Cassini-Huygens mission, which launched in 1997. So, 15, 16 years of work leading up to that launch. The Cassini-Huygens mission was a joint mission between NASA and the European Space Agency. It was 7 years in cruise, so it arrived in Saturn in 2004. Cassini was the orbiter, Huygens was the probe. You can see in this image when Cassini was at Cape Canaveral getting prepped for launch, the kind of circle that you see, the gold circle that's kind of front and center in this image, is the heat shield for the Huygens probe. One of the things that I always forget to point out in this image is that Cassini is not a cute little Mars rover. So the white things at the bottom are humans in bunny suits. And so Cassini is about the size of a school bus, so substantially larger than a cute little Mars rover. Cassini's mission was nearly 13 years, actually a little more than 13 years long. The end of mission was on September 15th in 2017 at approximately 7:55 a.m. Eastern time here in the United States. Cassini's mission was ended by intentionally crashing Cassini into Saturn. That was both to provide us with additional information about Saturn that we weren't able to get without actually entering its atmosphere, I guess, for lack of a better description, but also to protect some of the moons of Saturn that we know now have the possibility to harbor life. And so we wanted to make sure that we didn't contaminate them. The Cassini spacecraft carried 12 instruments. The Huygens probe carried 6. In both cases, this is a combination of remote sensing instruments, so spectrometers, cameras, those kinds of things that you're kind of used to in standard astronomy, but also things like mass spectrometers, plasma spectrometers that are in situ instruments that actually directly sample the material that we're interested in and ingest it into an instrument and measure it on the spacecraft. So this is just a pretty picture of the Saturn system that has to be in here for pretty picture reasons. It was taken by Cassini. This is, I like to call this Titan's baby picture. So this is the first picture that was taken of Titan by the Cassini spacecraft in April of 2004. This is actually before Cassini went into orbit around Saturn. And apparently nobody cared because this image was never processed. So this is just what it looks like even today. This is a much more recent picture of Titan. This is actually one of the last, towards the last pictures of Titan that were actually taken by Cassini, and we'll talk more about it in a second. This was taken on March 21st of 2017, and this was actually the last picture of Titan that was taken by Cassini on September 13th, 2017. Titan was actually used to fling Cassini into Saturn, because Titan's gravity was always used to kind of manage Cassini's orbits around Saturn during its tour. And also this last flyby then launched it on its collision course with Saturn. So we're gonna have to do some chemistry, and it's okay. We'll survive. So I mentioned that Titan's chemistry is driven by light from the sun. It's mostly driven by ultraviolet photons, so the same ones that, we have to worry about for skin cancer on Earth drive some really interesting chemistry on Titan. The main chemical reaction that's happening in Titan's atmosphere is this destruction of methane by light that then forms two molecules, C2H6, which is a molecule called ethane, and molecular hydrogen H2. This is actually a reaction that irreversibly destroys methane in about 100 million years because of the following reason. Titan's troposphere gets down to about 70 Kelvin. There are very, 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 very few things, like a couple noble gases, and that's it, that are still in the gas phase at 70 Kelvin. And so when the ethane reaches the tropopause, it condenses and rains out onto the surface. But there's never enough sunlight that reaches Titan's surface to be able to heat ethane up warm enough to send it back into the atmosphere. And so once the ethane condenses onto the surface, it's stuck there forever. And so that's a one-way trip. Hydrogen is also on a one-way trip. It's just a very different kind. Because Titan is small and its gravity is lower, it's about 1/7 that of Earth's, it actually can't hold on to hydrogen because hydrogen is so light. So the molecular hydrogen escapes into space, never to interact with Titan again. And so this is the main reaction that's happening on Titan all day, every day, right now, as we speak. There are some other ones happening though. So this is a slightly less simple version of the chemistry, although it's still an extremely simplified version of what's actually happening. You don't need to look at these. This is just to demonstrate that Titan's complicated. We can keep going. All of those things that I just waved my hands at result in the formation of these molecules. These are the 10 most abundant molecules in Titan's atmosphere. We already talked about most of them: methane, of course, hydrogen, carbon monoxide. Then we have ethane, acetylene, propane, ethylene, hydrogen cyanide, and carbon dioxide, and all of those are made by photochemistry, so chemistry that's being driven by light. But there's a bunch of other molecules that are being made in Titan's atmosphere too that were a big surprise. So prior to Cassini's arrival in the Saturn system, the largest molecule that had ever been detected in Titan's atmosphere was a molecule called benzene, which is C6H6. It has a mass of 78. The mass spectrometer that was carried by Cassini, that was specifically designed, its one sole purpose in life was to study the complex molecules in Titan's atmosphere, only went up to a mass of 100. And so we kind of thought that, flying through Titan's atmosphere, best case scenario, we would get data that kind of look like what I'm showing you right here. On the x-axis of this plot is just mass of the molecule, and on the y-axis, it's just number of some kind. Don't worry about the units there. In addition to the mass spectrometer, which was very specifically and expensively designed to study Titan's atmosphere as the only thing it cared about, Cassini was also carrying an instrument called the Cassini plasma spectrometer, which was not designed to study Titan at all. The Cassini plasma spectrometer was designed to study small but very energetic ions in Saturn's magnetosphere. So things like electrons and protons, and like if you're feeling really, really, really fancy, oxygen ions, but nothing big. However, when Cassini started flying through the top of Titan's atmosphere, which it did about 100 times during its mission, the Cassini plasma spectrometer was on. And we're really lucky that it was, because what I am showing you right now are actually not data from the mass spectrometer. It was a cropped version of the data from the plasma spectrometer, and this is the full version of the data. So the y-axis is logarithmic, which is not how chemists plot mass spectrometry data. It stresses them out a lot when you do this. But what we discovered from the Cassini plasma spectrometer is that there are ions in Titan's atmosphere that go up to a mass, not just a mass, but a mass to charge of about 10,000. Now, when you're in the ionosphere of a moon or a planet, like we are in these data, we're 950 kilometers above the surface. There's a lot of ions running around, and so you're going to expect an ion to carry more than one charge. So then we're talking about things that are maybe 20 or 30 or 40,000 AMU. So rather than having 6 or 7 carbon atoms like benzene does with a mass of 78, you're talking about things that have 7 or 800 carbon atoms, which is very, very different. So to give you a sense of scale, because I don't expect anybody to be a chemist, that's benzene, the thing that we thought was the most complicated molecule in Titan's atmosphere, the thing that drove NASA and ESA to spend $4.5 billion to send a spacecraft to the Saturn system, that molecule. The next thing I'm going to show you is not a real molecule. It's a thing that I drew in ChemDraw one day, but it's to give you a sense of scale. This is what something that weighs 10,000 would look like. So this is how wrong we were about the complexity of Titan's atmosphere, and this is how much more interesting Titan is than we already thought it was, that we already were willing to spend $4.5 billion to go learn more about. And so this has really changed our understanding of the kinds of chemistry that can happen in planetary atmospheres. It's really changed our understanding of Titan and Titan's role in our understanding of the origin of life, the evolution of life, and the possible search for life in the solar system and beyond. So the sad thing about that is that this instrument was not designed to study Titan. I mentioned that before. And so we actually can't identify any of the molecules in these data at all. We know that they're big and they're heavy and they're probably made out of carbon, and we don't know what they are. And we also can't use computer models to try to identify them, which is something that I spent a lot of time in grad school trying to do at the beginning, because we just don't have enough information about all of the chemical reactions required to build molecules that are this heavy. And so one thing that we can do, if we can't use our data, which is usually our, first line of defense, the thing that we would most like to actually use to study the place, and we also can't use our models, we have another tool in our toolkit, which is to use laboratory experiments. And this is something that my group does. And so I just want to mention it quickly so you can get a sense of what I actually do on a day-to-day basis, which is actually mostly email. But I used to do experiments. Now my research group does. So the way these experiments work, and you may have heard of similar experiments before, because these experiments are the direct descendant of the very famous Miller-Urey experiments trying to study the origin of life on Earth, and then also the direct descendants of experiments that were started by Carl Sagan and a research scientist in his research group named Bishankare in the late 70s, early 80s. So the way that these experiments work basically is you take simple abundant gases. So usually we would use the main constituents of an atmosphere. So in the case of a Titan experiment, we would use things like methane and nitrogen. If you're feeling really fancy, maybe we'll put some carbon monoxide in there. You expose them to an energy source. Over the decades, these experiments have been driven by literally any energy source you could possibly imagine. Someone has done it at some point. At this point, we mostly just use ultraviolet photons and energetic plasmas to initiate the chemistry, kind of mimicking the sun and the energetic photons that come from the sun. Depending on what you start with, you will do the photochemistry that we talked about before and probably end up with a complex organic solid. This one is a suspiciously Titan color, which is not surprising because this was a Titan experiment that generated these solids. And then you can do whatever you want with the solids and study them. And so the whole reason I'm telling you this story is because we started doing these experiments to try to understand what these really complicated molecules that were seen by the Cassini plasma spectrometer might actually be. And so we analyze these, and what we find is there's like tens of thousands of different kinds of molecules in them. And so we pick out just a few that are interesting for astrobiology and origin of life chemistry to emphasize here. And so I had mentioned that we're really interested in things like nucleobases. And so in this material, we see the familiar ATCGU of DNA and RNA. And also in this particular experiment, we found the 2 smallest amino acids, so the 2 smallest building blocks of proteins, glycine and alanine. Also to mention that adenine is, in addition to being one of the building blocks of DNA and RNA, it's also a piece of the molecule adenosine triphosphate, or ATP, which is a source of energy for all of life on Earth. And so these are molecules that are really important when we're thinking about origin of life chemistry on Earth. Okay, back to Titan. So I'm going to walk you through some of the things that we learned about Titan from Cassini. And the first thing that we learned is that even if you spend $4.5 billion, if you take a picture of Titan in visible light, it still looks like a fuzzy orange ball. It turns out that the Voyager image processor processing. Titan's probably more of like a yellowy brown color. We were also able to study Titan's kind of distinctive haze layers in greater detail. And so here you can see some structure that's probably caused by dynamics in the atmosphere. We believe that the haze layers are made out of all of those chemistry words that I mentioned before, hydrocarbons, nitriles, blah, 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 blah. I mentioned that we're very close to the triple point of methane on Titan, and that does actually enable a methane cycle that's very similar to the water cycle here on Earth. And so this is an image of some methane clouds that were taken near Titan's south pole. So we know that there are clouds and indeed rain on Titan. Those are made primarily out of methane and ethane, although Titan has many flavors of clouds. There is also there's been some evidence of benzene clouds. There's been evidence of hydrogen cyanide clouds, actually a huge hydrogen cyanide cloud at the South Pole, and a number of other flavors of clouds, some of which have yet to be identified. We know they exist, but we don't know what the composition is. So if you think it's tricky to study the composition of Titan, you should try studying the composition of an extrasolar planet. Luckily this time, we learned some lessons from Voyager, and Cassini's camera was equipped with special narrow wavelength filters that were able to see through the methane and the haze in Titan's atmosphere down to the surface. And so that's what Titan's surface looks like. I showed you this image earlier and I didn't describe it to you at all, but I'm going to fix that problem right now. So Titan's surface is actually pretty heterogeneous. We divide it kind of broadly into two categories of terrain that are very importantly scientific. So one category of terrain is the dark stuff, and the other category of terrain is the light stuff. The light stuff is still mostly an open question. We think that it's probably mostly water ice, but we don't really understand it very well. Um, I lied to you, there's actually three kinds of terrain because the dark stuff comes in two flavors. If you are at the equator, mid-latitudes in the south to mid-latitudes in the north, all of the dark stuff that you're seeing in this image are extensive sand dunes. And I'm going to show you a close-up radar image in a second. If you are at the North Pole, all of the dark stuff are large lakes and seas, which I will also show you in a second. This is an image from the surface that was taken of the Huygens probe. We think that the surface is made primarily out of water ice, although there might be an ammonia component. If you look at this image for more than 2 seconds, you might be wondering if you have landed on Earth or Mars instead. These are cobbles that are about 10 centimeters across. They're very close to the camera, which is why they look much larger than that. But they are rounded, indicating that they have undergone erosion from processes of liquid moving across Titan's surface, so very reminiscent of Earth, of Mars. We tend to think of the area where the Huygens probe landed now as being similar to some of the regions in the desert southwest of the United States, where it is extremely, extremely dry the absolute vast majority of the year. But when it does rain, there are absolutely torrential downpours that cause localized flash flooding. And we think that that is what happens in this region of Titan, and not just because the camera was built in an area where this happens, but also because scientifically we think that's what's going on. So that's what the surface looked like from a camera. These are the lakes at the North Pole from Cassini radar. When you're looking at radar, you have to kind of sort your brain out for a second because this isn't really an image. What you're looking at is that things that are dark in radar are smooth at the wavelength of the radar. So Cassini's radar was 2.2 centimeters. So everything that's dark in this image is smooth at 2.2 centimeters. Things that are bright are rough at 2.2 centimeters. Now, the only thing really in the universe that is this smooth at 2.2 centimeters is a liquid. And so we know that these are large lakes and seas, and from extensive study now we've been able to do things like bathymetry of these lakes from radar reflections that have actually gone all the way through the lake, bounced off the bottom of the lake, and then gone back up to the spacecraft. So we know how deep they are in places. We've been able to map them. They're very large. They're about the same size as the Great Lakes in the United States here on Earth. And we think that this is a place that's really interesting for potential subsequent chemistry because this material that's made in the atmosphere will eventually get deposited in the lakes. Some of it will dissolve and perhaps undergo subsequent reactions. Some of it will not be able to dissolve and will either end up as some kind of like floating gunk on the surface of the lake or perhaps actually precipitate down and end up in contact with the water ice bedrock below. But this is definitely a place that's really interesting, and we would all very, very much like to send a fish finder to the lakes to see if there's anything swimming around in them. I mentioned the sand seas, so this is Cassini radar now of the extensive sand dunes. Um, Sand is a weird concept on Titan. I told you already that all of the rock is in the middle of Titan. There is nothing that we think of as rock on Titan's surface. Titan sand dunes are made out of organic molecules that were created in the atmosphere. We do not understand the processes that result in the formation of these sand grains. One of my former graduate students spent her entire PhD trying to figure it out. She definitely made some progress, but we're still a little stumped. And finally, the other place that I want to mention, which is really important for Dragonfly, which I'm going to talk about in a second, are impact craters. So this is an impact crater called Selk, which I wish I had like a good way. Can you see my arrow? Probably not. No. Oh, you can't see my arrow. Okay. Well, the thing that I'm pointing at right now is Selk in the image. And so the thing that's cool about impact craters is that because the surface is made out of water ice, when you have an energetic impact, it's going to melt all of that water ice. And when it does, it creates an impact melt pool that can actually persist for tens of thousands of years because the top of the impact melt pool flash freezes because it's so cold on Titan. That actually acts to insulate the bottom of the impact pool, just like if you have a lake or a pond here on Earth in the winter, the top freezes over, the liquid stays liquid for quite a long time. And so this is a place where a lot of really interesting chemistry can happen. And so all of that material that was made in Titan's atmosphere that has probably never seen a water molecule in its whole entire life gets to hang out with a bunch of water molecules for 10,000 years and do a bunch of really interesting chemistry that has been shown in the lab to result in the formation of a bunch of molecules that are really interesting for astrobiology reasons. I'm gonna skip some slides. Well, I'm not gonna skip this slide. Um, I just want to emphasize one of the things that's been really challenging about trying to plan future exploration of Titan is that we actually don't know that much about the surface, even though we sent a probe to the surface. Titan's surface has been really enigmatic, and so this is actually from the whiteboard at my undergrad alma mater, Caltech. So before the Huygens probe landed on Titan, they had a betting pool of what will the Huygens probe land in or on. Most of the people picked some kind of boring things like ice. Okay, yeah, tar, fine, whatever. Like one person was like, hey, we might land in liquid. Like, okay, great. Most of the people were extremely boring and were like, we're not going to be able to tell what it is. Um, you probably can't read it very well, but the bottom of the undeterminable category, someone wrote in parentheses, it'll be tar, but we can't tell. Um, two extremely pessimistic people wrote that it was going to be dead on arrival, and one extremely optimistic person wrote that it was going to get eaten. We would have all very much liked to have the answer to have been eaten because that would have made Titan extremely interesting. It turns out that the answer is probably annoyingly the person who wrote it'll be tar, but we can't tell. That MEB person is someone you may have heard of. That's my undergrad research advisor, Mike Brown, who is famously known as Pluto Killer. Um, oh, now my slides won't advance. Love that for us. Okay. This image is just in here because if you've never seen it before, you should. I'm on a one-person mission to make sure all of humankind has seen this image. So this is a sun glint off of an extraterrestrial lake, our first sun glint off of another world. This was taken by the visible and infrared mapping spectrometer on Cassini. At the time that this image was taken, they were able to use kind of all the spacecraft trajectory and geometry and stuff that you learned in school at some point to figure out which lake this reflection came off of. And it turned out that that particular lake did not have a name yet. The lakes on Titan are required to be named after lakes on Earth, which does not result in any confusion whatsoever for people who study lakes. And so this particular lake is now called Jingpo Lacus, which means mirror lake, which people thought was appropriate. And I just always feel like everybody should see this image because it still gives me chills, even though I've seen it about 10 billion times at this point in my career. Okay, so Titan turns out to be really interesting. It has what we consider to be all of the key ingredients that are necessary for life. So we have energy. There is not as much solar energy as there is here on Earth. Titan is farther from the sun than the Earth is, so only gets about 10% of the sunlight that we get here on Earth. And then of that 10% that's incident on the top of Titan's atmosphere, only about 10% of that actually makes it down to the surface. So the brightest it ever gets on Titan is kind of like dusk on Earth. Or also like if there's a full moon on a clear night, that's also a decent analogy of the brightest that it gets on Titan. So there's not a ton of sunlight. But it's also possible that creatures would be able to take advantage of these molecules that the photochemistry is making. And so the sunlight is actually converted into chemical energy that then precipitates onto the surface. And if there were creative creatures, they might be able to figure out how to use it. The second thing that we think of as being an important ingredient necessary for life is organic material. Titan's surface is literally made out of organic material, so we do not have any concerns about the abundance of organic material when it comes to looking for life. The other thing that we consider to be kind of our third important ingredient for life is liquid. We tend to think of water as being the most important liquid. We don't know if that's, if there's good astrobiology reasons for that, or if it's just a bias because that's what life on Earth uses. Titan does have liquid water, so I've been talking to you about Titan for like almost 40 minutes, and I have not mentioned the fact that Titan has a subsurface liquid water ocean. We always forget to tell people it's like the least interesting thing about Titan, but it does. So just like Europa and Enceladus and a lot of the other icy satellites in the solar system, Titan also has a subsurface liquid water ocean. Additionally, there's been liquid water available on Titan's past, like I mentioned, in these impact melt pools and potentially also cryovolcanic flows. However, Titan is so interesting. It actually has two liquids, not just one, because it also has those methane lakes that I mentioned before in this active methane cycle. And so there's been people who've been actively trying to study, is it possible that there could be life that's based on liquid methane rather than liquid water? And wouldn't that be interesting if Titan had two completely different biospheres based on two completely different biochemistries, one that used water and one that used methane? So on Titan alone, we can study prebiotic chemistry in the context of this place where there's all of these Earth-like surface processes happening. There's rivers and lakes and seas, there's rainbows, there's sand dunes, there's all of these processes that we associate it very, very strongly with Earth, and they're happening on another planet where there's also really interesting prebiotic chemistry happening. So what's next? So I'm gonna just talk to you for a few more minutes about what we're doing next, which is Dragonfly. Dragonfly is a mission to explore Titan's prebiotic chemistry and habitability using a mobile platform. So I mentioned to you that Titan's gravity is less than Earth. It's about 1/7 of Earth's, and its atmosphere is about 4 times denser than Earth's. That's a combination of the pressure being higher, but also the temperature being much colder. It is substantially easier to fly on Titan than it is to fly on Earth. If you personally found yourself standing on the surface of Titan, and if that ever happens to you, please call me because I have a really lot of questions that I need answered. If you had wings, I don't know, like some sturdy cardboard, maybe balsa wood, and you just like duct taped them to your arms and flapped your arms, you could fly on Titan under your own power. It's that easy to fly on Titan. And so Dragonfly is going to take advantage of that. We're going to operate very much like the Mars rovers. We're very much Mars rover-like in our mass and our size, but we're taking advantage of the fact that it is much easier to fly than it is to drive on Titan, and that's going to be able to help us access all of those different really interesting surface features that I mentioned. We're going to do measurements on the surface of composition, geology, meteorology, and also search for seismic activity. And then while we're flying, we'll be able to do a lot of aerial imaging that's going to help us understand more about Titan's surface geology and also help us make sure that our landing sites are safe. Um, we have three kind of big picture science goals with Dragonfly. So one is to try to understand this prebiotic chemistry that I've now mentioned 9,000 times. We're also interested in trying to understand Titan's habitable environments by doing things like measuring atmospheric conditions, trying to understand how methane is transported on the surface, and also really interested in understanding how liquid water has interacted with the Titan environment, surface environment, both in the recent past and in the much longer past, both from impact craters and also from the subsurface liquid water ocean. And of course, we would be remiss while we're sitting there with the most technologically advanced mass spectrometer that will have ever flown in space if we didn't search for biosignatures. And so we will be searching for chemical evidence of water or hydrocarbon-based life. At this point, I am contractually obligated to tell you that Dragonfly is not a life detection mission. However, we will be searching for signs of life if they should decide to present themselves to us. We are going to be looking at a bunch of different types of materials, and the way that we're doing this is through our landing site selection. So I mentioned Salt Crater and pointed out where it was on Titan. That was not for no reason. Salt Crater is our landing site. So we will be landing a little bit south of Salt Crater in this interdunes region that's shown in this mock-up of Cassini data that was made by combining instruments, data from a couple of different instruments. The reason that we're going to be landing in the inner dunes, we do not have high-resolution imaging like we do of Mars. We cannot say, go land right in that spot right there. We know it's safe. And so instead, we're having to use the laws of physics to figure out where is safe. And one of the things that we know from the laws of physics and from studying dunes on Earth is that interdune regions, the spaces between dunes, tend to be really boring. They tend to be very flat. They tend to be uniformly size sorted, a really good place to send a spacecraft when you do not know what your landing site looks like. And so there's an interdunes region on Earth shown in this image. You can tell that it's Earth because there's people there. As far as we know, there are no people on Titan. And so we're going to be going to a region like that. Once we land there safely, then we will make our way towards Salt Crater. And in the process, we'll be able to study dunes, interdunes, impact crater deposits, and also be able to sample places where liquid water at some point in Titan's past interacted with the organics that were made in the atmosphere and underwent this chemistry that we think is really interesting for prebiotic reasons. Um, a lot of stuff on the slide is already out of date. But our mission, our nominal mission actually lasts a little over 3 years. We are going to fly as far as we can. This traverse distance was optimistic. We are probably not going to fly that far, but we are going to be able to examine something like 20 to 30 unique landing sites during that 3 years of exploration. And then people are always going to ask me if we're going to go into extended mission. And the answer is yes, of course. As long as the spacecraft is operating correctly and NASA still exists, we will go into extended mission as long as NASA will let us. I always used to joke about that, and it feels a little bit less like a joke these days. Anyway, just a couple other things about Dragonfly, and then I'll stop so that you can ask questions. Dragonfly is carrying a number of different instruments. DRAMS is the mass spectrometer. That's really our workhorse instrument because we are so interested in trying to understand Titan's chemistry. That is the instrument that I will be working on the data from the most, and those are the data that I am the most excited about. Paired very closely with DRAMS is Draco, which is our drill for acquisition of complex organics. Draco is a drill that's mounted on the skid that's going to drill into the near surface and ingest the material that will then go into DRAMS for us to study. Dragons is the coolest named instrument that NASA will have ever flown. Stands for Dragonfly Gamma Ray Neutron Spectrometer. Dragons is going to give us bulk composition information underneath us wherever we land. So it's not going to tell us specific molecules, but it'll tell us, oh, in this pot, like this spot really has a lot of carbon under you, or in this spot there's really a lot of oxygen under you, which probably means there's a lot of water under us. That's also going to help us decide in any given place whether or not we want to drill. There are pieces of the way that DRAMS operates that are consumables, and so we'll only be able to do them a certain number of times. And so if we land somewhere and that place looks exactly to Dragons, like the last place we landed, then we might make the decision not to do DRAMS measurements there because we'll assume that we've already sampled material that was similar at a different landing site. DragMet is our geophysics and meteorology package. You don't often see those two words next to each other in an instrument, but DragMet really is a suite of a whole bunch of different sensors: our methane relative humidity sensor, temperature, pressure, wind speed, wind direction, and also our seismology package to help us look for earthquakes. They're put together as one instrument, even though they're a suite of sensors because they kind of share one brain inside the spacecraft. And then finally, Dragon Cam is our camera suite that's everything from a microscopic imager that's going to help us look at the material that gets drilled by Draco to the cameras that are going to be used while we're doing our aerial flight to help us do aerial imaging. I'm skipping all of these. I already said actually most of this. They're mostly just backup slides. We'll see if the video can work. Okay, so this is an artist's conception of the most stressful day of my life. So we will arrive at Titan in 2034. We descend on parachute to about 1 kilometer above the surface, and then the parachute releases us with the very extreme hope that we are actually capable of flying. We will fly to our landing site in that inner dunes region south of Salt Crater. Once we land, we will spend actually quite a bit of time at our first landing site doing what's called commissioning of our instruments to make sure they all work. So this is a very unrealistic representation of how much time we're going to spend at our first landing site. Once we are done checking out the instruments, then we will take off and fly to our next landing site. I want to see if I can go back for a second. Oh, I stopped at the perfect spot. It's like I've done this before. So a couple of other things to point out about dragonflies. So I mentioned that we're about the size of a Mars rover. So we're about 10 feet long. I realize these are the wrong units for you. I'm so sorry. We're about 10 feet long and about 5 feet tall. So we're about 1 Sarah tall, and about 2 Sarahs long. And we're about the mass of a car, a small car, a small, like normal people car, not a small American car. And so that's just to give you a sense of scale. This kind of circular disc that's pointed up and that, hinged over to fly is our high gain antenna. So we don't have an orbiter to relay back to Earth the way that the Mars rovers do. And so we're doing what's called direct to Earth communication from our high gain antenna. This also limits when we're actually capable of talking to Earth. Titan is tidally locked to Saturn, and so we're actually only able to talk to Dragonfly when we can see Dragonfly, which requires being able to see that part of Titan. And so Dragonfly will actually spend quite a bit of its mission out of communication with Earth, which is not even just a little bit stressful. And then the other thing I wanted to point out about this, because people always ask about it, Dragonfly is powered by a radioisotope thermonuclear generator, just like we have on a couple of the Mars rovers, just like powered Cassini, New Horizons, all of our outer solar system explorers. That radioisotope source will trickle charge a battery. We're actually basically a flying battery. I think our battery weighs 300 pounds. And it's actually just most of the spacecraft. So we're like a flying battery with legs and a couple of instruments that we manage to like smush into various places. And then just two things real quick. I really need to update this slide. I'm not on Twitter anymore. If you look for me on Twitter, you will be sad because I am not there anymore. But I use the exact same handle on Blue Sky, and so you can look for me there instead if you happen to be on Blue Sky. If you have questions, you can also shoot me an email. I will answer them in somewhere between 30 seconds and about a year, depending on what question you ask me and what my email looks like. If you are now madly in love with Titan and you want to know more about it, there are two fantastic books about Titan that were both written by one of the scientists on the Dragonfly mission named Ralph Lorenz. The first one is called Lifting Titan's Veil. It's a lot about the development of Cassini. So it was written kind of right around, I guess, prior to Cassini's launch, and talks about everything I just told you up until Cassini and also how kind of behind the scenes of how Cassini got made. And then Titan Unveiled was written a few years into the Cassini mission, and kind of talks about all of the things that we learned from Cassini that we didn't know ahead of time. They're both really great books, and I highly recommend them if you are interested in knowing more about Titan. And with that, I would love to take any questions that people have with whatever time we have left.
Thank you very much, Sarah. That was absolutely wonderful. And just before we move on to the questions, if I could ask people to unmute and thank Sarah for her talk in the usual fashion. And just to kick things off, I see that we have a question already in Zoom. But before we do that, just a question of my own. Obviously, we had a tremendous amount of success with flying on Mars, which was much more difficult, as you've already pointed out. Um, but I was puzzling that a lot of the images taken from space and from Earth-based instruments uh, did not reveal. It wasn't easy to see anything on Titan's surface. So, do we know how much horizontal and vertical visibility there will be for scooting around in the air without running into things like hillsides and so on?
Yeah. It's not as bad as you might think. We actually had what started out kind of as just like a reading group with a bunch of grad students when I very first started out as a professor, ended up being a paper that they all wrote together because they had the exact same question. And this was before like Dragonfly was like the idea even remotely existed. And so some grad students sat down and did the calculations. I don't remember the numbers off the top of my head, but we have decent visibility. It's like Earth on kind of like a normal-ish day. The thing that really gets you when you're trying to look at Titan surface from space is just the path length. Because when you're looking through all of that methane and haze particles, it really gets you. But on the surface, the visibility be too bad. And you can kind of notice that a little bit in the images from the Huygens probe, although it's really hard to tell scale. But when you look off in the distance, you're not immediately just hit with this wall of gunk that's telling you that you can't see anything. So we don't envision any kinds of those kinds of issues. Titan also doesn't have a ton of topography, so hopefully we don't have to worry too much about crashing into the side of a mountain. There aren't very many of them. Water ice doesn't support topography nearly as well as rock does, as it turns out. So we don't have to worry about that as much. The other thing people always ask us about, because they're used to flying their drones at home, is like, aren't you worried about trees or telephone poles? And I'm like, if we crash into a tree or a telephone pole, we will absolutely consider this mission to be a huge success. Screw all of the other scientific goals that we had. Like, we will be perfectly content. As long as we know that the thing we crashed into is a tree or a telephone pole, we will be super happy. Like no complaints from us.
Great stuff. Thank you very much. Okay, so Peter, do you want to
Yeah,
talk through some of the questions?
I had a quick one just before Scotty's got a question there. Uh, is it fully committed, the project? Is it all signed up and nailed down?
Yeah, that's a really good question. So right now we are we're in what's called phase C. So the way that NASA missions work is like phase A and B are what's called I've now completely forgotten the word that we actually use, but it's basically like the design phase.
Mm.
And you're doing a lot of reviews and doing all those kinds of things. And when you move into phase C is the beginning of implementation. Um, phase D is kind of everything that leads up to launch. Phase E is the science phase. And so we're in phase C right now. We're building flight hardware. We just last week, that feels true. This has been a weird month. Last week we underwent our final big review, which is called CDR. It's the Critical Design Review. And so we just underwent that last really big review, which is effectively the last huge hurdle before launch. There are other reviews that actually allow us to launch, but this was the really big one, and it went quite well. So we are happening. Um, Barring all of the things you've been seeing on the news. Um, but as of now, we have our funding committed. We're a real mission that is marching towards the launch pad. So I didn't mention that our nominal launch date right now is in 2028. So we're about 3 years out from launch right now, which can both sound like a really long time and a really short time, depending on which engineer you're talking to. But we are, we're getting close, which is it's wild. Time flies because we first started working on this mission in 2016, 2017. And that kind of feels a little bit like yesterday, but it very clearly is not.
Okay, thank you. Scotty, do you want to ask your question?
Yeah, sure. Yeah, thank you very much. And thank you very much, Sarah. That was a fantastic presentation. Very much enjoyed that. So just a quick question, really. I'm just wondering your thoughts on if cryovolcanism is still a process that may be going on in Titan, and if so, could that be an explanation for how the methane continues to be topped up?
Yeah. That kind of question is like one of the fastest ways to get Titan scientists yelling at each other. Um, we really don't know the answer. We still have not mapped the surface in super good detail. We have pretty low resolution imaging data of most, if not all, of the surface at this point. But in terms of our higher resolution imaging data and then the radar, which really gives us our best information about the surface, we don't have full surface coverage. Of everything we have seen on the surface, there's only really one area that seems to be kind of have held up all of the tests that everyone came up with to have, kind of morphological evidence of cryovolcanism. But that evidence seems to be pretty strong in that one location. So I think everybody kind of agrees like that place seems to indicate that it's possible. If it does happen, that would certainly be one explanation for the replenishment of methane in the atmosphere. The question is whether or not it could happen frequently enough to do it, and whether or not it's something that's still occurring at this point in Titan's history. We would absolutely have loved to, have seen a volcano erupt during the Cassini mission. That would certainly have solved a lot of our arguments, and unfortunately, that did not happen. One of the cool things about Dragonfly that if we get lucky would be really neat to see is that we do have this methane sensor. And so one potential thing that we could end up doing with Dragonfly, depending on what we see from the methane sensor, would be to chase a gradient. So if we started flying in a direction and suddenly noticed that the methane abundance was increasing, that might be something that would lead the team to continue trying to chase that gradient to see if we could find the source. You could envision some kind of vents of the scale that we would never have seen from Cassini that could be releasing methane, that would be, related to the same types of processes that could result in cryovolcanism. So this is definitely an open question. And, I would say it is probably the biggest question that we really had about Titan prior to Cassini that we didn't answer, which is very frustrating to everybody.
Awesome. Thank you so much.
All right. We have a question from Jim Barron.
Yes, thanks again for the talk, Sarah. You talked about the subsurface water ocean being liquid. What's thought to keep it liquid? What energy source? Any thoughts on that?
Sorry for the dogs. Yeah, that's a great question. So it definitely has to have some kind of antifreeze in it for sure, just like all of the other subsurface oceans in the outer solar system. That could be ammonia is one of the things that's been something that people have thought about. It could also just be very salty, which is another potential explanation. It also could be the word liquid might be doing a lot of work. It's definitely not solid all the way through, right? We have, similar to Europa, although from a different line of evidence, we have evidence of a subsurface conducting layer that is almost certainly liquid water. In terms of the energy source, I would say in a lot of ways that's still kind of an open question. There's some arguments that can be made from orbital dynamics that make sense. Titan's orbit is not circular. It's almost circular, but it's not circular, and you would definitely expect it to be circular at this point in solar system history. So there's definitely something that has gone on there that has maintained this little bit of eccentricity in Titan's orbit that could be related to it. There's also a bunch of other kind of weird things that happen if you try to model Titan's geologic history in terms of differentiation and stuff like that could have resulted in large releases of heat relatively recent in solar system history, talking about like hundreds of millions of years ago, that could still kind of be remnant there and keeping the ocean liquid. But I think one of the things that's kind of been interesting about the history of kind of last 20 years of solar system exploration is we keep finding oceans in places we don't expect them. It took people a really, really, really long time to come up with an explanation for how Enceladus could possibly have a liquid water ocean. And in the end, it almost always comes down to weird things about orbital dynamics that we just didn't have enough information about that end up being the explanation.
Thanks very much.
That's all the questions on Zoom, Nigel.
Thank you very much. Any questions on YouTube at all?
Yes, we got 2 or 3 questions, if that's okay to
Yeah,
ask.
by the way, Will.
Okay, excellent talk. There's been quite a few watches, Dr. Hörst, and a bit of banter going on as well, which is always good to see. So there's a little bit of chat about possible contamination and stuff. And so there's one question from Roger. You said that Cassini was crashed into Saturn to avoid contamination of the satellites, but did you not say that Huygens landed on Titan? So I presume, is there a difference with Cassini? Was that a big issue from contamination? Were there things in the mission there which is different to Huygens, for example?
Yeah, so basically what happens is that NASA and ESA similarly, and all of the space agencies, because they're all signatories to the treaty that requires this, have offices of planetary protection. Each object in the solar system has a planetary protection classification that is basically determined by whether or not we think that Earth life could survive there. So if like we had some tardigrades hitch a ride on a spacecraft, could they like make a nice home and start a new, happy little tardigrade colony on a different planet? And also if we think that it's possible that that planet could have its own indigenous life. And so that kind of determines how careful we are with that world. These categories also apply for bringing samples back. So that's just a whole nother extra level of care because we don't like to have some kind of Andromeda strain situation happening here on Earth. And so once we know where we're going, then the particular mission has to negotiate with the Planetary Protection Office of its respective space agency about what is actually required to meet the planetary protection requirements for that particular location. So because the Huygens probe was landing on Titan on purpose, it had different planetary protection rules than the Cassini spacecraft did. Originally, when Cassini went to the Saturn system, the only moon that we really thought we had to worry about in terms of harboring life was Titan. And so it was going to be relatively straightforward to make sure that we didn't hit Titan, because we could use Titan to do whatever we wanted, use Titan's gravity to do whatever we wanted with Cassini at the end of the mission. In the course of the Cassini mission, of course, we discovered that Enceladus is also wildly interesting, and has the possibility to have its own life, but also could possibly harbor Earth life if it were to become contaminated. And so the decision was made that it was far too risky to try to put Cassini on a course that would just let it decay naturally and eventually crash into Saturn, because there was too much of a chance that it might hit Enceladus on the way. And so they decided instead to intentionally crash it into Saturn, doing a bunch of really cool science along the way. We did mass spec, we got really great gravity data, we got really great information from the magnetometer, and from some of the other instruments. And so it really was basically a whole new mission. There were tons of papers. We were involved in the mass spec papers, so we got some really good science. There also at some point had been some discussion of actually trying to leave the Saturn system with Cassini's remaining fuel. But in the end, it was decided to use that fuel to do more exploration of the Saturn system rather than trying to go off on another adventure. And then, of course, because Dragonfly's entire point is to go there and look at organics and kind of assess the conditions for life and stuff like that, we also have very high planetary protection classification at play. And so we work very closely with NASA's Planetary Protection Office to make sure that we don't carry any contamination with us when we land on Titan.
That's no, fantastic. It's actually news to me to hear about different sort of alert status, sort of different criteria for space missions. I would have been under the assumption that all space missions would have been incredibly clean. Just for
Not
like,
even a little bit. You can, if you're interested, I think if you just Google like planetary protection categories or something like that, the Wikipedia article on it is actually really nice. That's generally where I send my students when we talk about this in class. And so you can see like where all of the different planets, which classification they fit in. And if you do go look at that, you will see that Titan is one of the hotly debated places, because there's a lot of disagreement about what planetary protection status Titan should have. And so that made the negotiations even a little bit more complicated for Dragonfly than they normally are. But you'll see like the sun, for example, is the lowest planetary protection classification because we don't think that Earth life could survive there. And we don't think that the sun has its own life. And so when we launch solar missions like Solar Probe Plus and stuff like that, we don't really have to worry about sterilizing the spacecraft because we don't have any concerns about ruining the sun. So it's definitely something that's really cool. It's actually, it's really neat. Like NASA employs a bunch of biologists and they're in the clean rooms. They swab spacecraft surfaces, they swab, the tools that are being used in there and all these kinds of things. And they take them back and they culture them and see like, does anything grow? And if something grows, they go back and they say, okay, we got to clean this up again. And there's lots of different techniques that are used to sterilize the spacecraft depending on what materials it's made out of and what the instrument sensitivities are and all this kind of stuff. So it's really like planetary protection is its own like scientific field, and the work is really interesting.
Wow, that's amazing.
There was, of course, life in the sun and Project Hail Mary.
I know. Yeah, that would completely ruin our entire planetary protection philosophy if Project Hail Mary turned out to be true.
And we've got a question from Zapfan. Are you going to take mass specs and other measurements during flights for measuring at different altitudes?
Womp womp. No. So, no is the short answer. The slightly longer answer is that originally it had been our hope that we would be able to do some of that. It was always going to be really challenging because the two most energy intensive things that we do as a spacecraft are fly and do mass spectrometry measurements. And so doing them at the same time was always going to be something that would be really challenging. At this point, sorry, hey, shh. It's really windy and they keep barking at the wind. Gizmo, stop. The issue at this point isn't just that it would be challenging because of the power requirements. It's actually not possible. The atmospheric inlet that we originally were going to have on the spacecraft was de-scoped during the development process because it was adding too much complexity to the mass spectrometer system to be able to do atmospheric measurements. So we actually can't even do atmospheric measurements while we're sitting on the ground, which is a huge bummer after I just told you how cool Titan's atmosphere is. We can do specific molecules using sensors on Dragnet. So we can do the methane, we can measure the methane abundance and we can measure the hydrogen abundance. And we can do that. I think we can still do that in flight. But we're not gonna be able to do mass spec while we fly, which makes me very sad because it would have been really cool. But that's what happens when you build a space robot. You lose a lot of cool capabilities along the way.
Right. And do we have time for one more question? Would it be okay, Nigel?
Yep, go for it.
Oh, we got one from Graham Darling. Do we have any idea how the giant dunes were made and what the process is for the creation of the sand? I remember you saying that there was someone who did a PhD about the creation of sand and they didn't work it out, but I wondered if you could just enlarge on about the dunes and the sand.
Yeah. So there's two kind of big picture ideas about how the dunes form. So one is kind of like sticking small things together to make them bigger, and one is taking a big thing and breaking it down into smaller pieces. And so in both cases, we have organics raining down from the surface or from the atmosphere onto the surface. So the question is, do the organics somehow stick together through whatever process and get big enough to form the dune particles? Because, and I realized I didn't say this before, the organics, when they end up on the surface, are much smaller than the sand particles. And so it's not just the particles that have fallen onto the surface. Something has to happen to them. The other option is that the organics come down onto the surface and form basically like a sedimentary rock, if you can think about that process, and they lithify. And then erosional processes break them down into sand particles. It could be both of those things are happening. There's also been some proposals that the lakes might be involved. So there's this process called flocculation, where you basically have bubbles bursting, and that can generate particles. I think that's probably less likely. The dunes are globally uniform. They're everywhere. And so that really speaks to a process that is happening globally, because one thing that my grad student did find is that the sand on Titan is probably very soft. and probably cannot tolerate being transported for long distances. And so that would really tell you that the sand has to be made effectively where we see it, which would tell us that it's a global process and probably then does not involve the lakes because the lakes are located at the North Pole. In terms of the actual formation, it's very similar to Earth in that, there's winds that get to be sufficiently high speed to transport the material. The one big difference from what we see on Earth is that as far as we can tell, and this was very confusing at the beginning of the Cassini mission, I remember a lot of discussions where people were like, what is going on? In most locations on Earth, the dunes record the prevailing wind direction, or directions if it's multiple directions, as that causes some types of dunes to form. On Titan, as far as we can tell, the dunes do not record the prevailing wind direction because the prevailing winds are actually very, very low, which is one of the reasons why Titan is a good place to fly because it's just not windy there most of the time. Instead, what we think happens is that near equinox, the direction of the circulation of the atmosphere switches. And in the short period of time in which it's undergoing that switch, the weather gets like batshit crazy, like torrential downpours, really, really large windstorms, super high wind speeds. And we think that the dunes record like that very short period of time. And so the thing that's really weird about Titan's surface, we think, is that most of the surface features record the catastrophic things that happen on the surface. And the day-to-day things that are happening on Titan don't really leave anything on the surface in terms of a record. Earth is a combination of those things. Obviously, catastrophic things happen here also that are recorded by the surface, but our surface also records like just kind of our day-to-day normal, and it doesn't seem like Titan does that.
Well, thank you very much. It's all from YouTube. Excellent, excellent. Thank you.
Thank you very much. I just, while you were talking there that last time, Sarah, I noticed another question came up from Karen Martin on the Zoom, which you managed to answer without having had the question. Karen was asking.
It's the Professor Spidey sense. Like I sense
Yeah.
when the question's coming and I just answer it ahead of time.
Yeah, and it's her question was, would there be windy conditions on Titan, bearing in mind the thickness of the atmosphere? And you'd already by that time had said it wasn't windy at all on Titan. So I hope that's okay for you, Karen. And just before we wind up for the evening, I would ask everybody to unmute again and thank Sarah for an excellent, excellent presentation. Thank you.
Thank you. Thank you so much for your attention. I know it's hard on a Friday evening.
That's
Thank you
great.
very much.
I'm also very delighted to have a professor on board who uses phrases like batshit crazy. I think that
I really toned it down a lot. My students would tell you that I curse a lot.
I think that's
I try to
absolutely.
behave myself when I give public talks, and it doesn't always work.
Well, I think that is absolutely splendid. So, thank you everybody for attending, and we'll see you at the next meeting at the first Friday of May. And thanks again, Sarah, and good night, everybody.